Travel back to a time when Earth had never seen green. There are no forests breathing, no leaves turning toward the sun, no grass covering the land, and no oxygen filling the sky. More than 3 billion years ago, our planet exists in a radically different state. The oceans are dark and heavy, saturated with dissolved minerals. The atmosphere is thick, hazy, and chemically hostile. The surface is ruled entirely by microscopic life that survives without light. The sun still rises every day, pouring vast amounts of energy onto the planet. Photons strike the oceans, the land, and the atmosphere in staggering numbers. But for hundreds of millions of years, that energy goes largely unused. Life persists by feeding on chemical reactions alone. It survives, but it does not yet exploit the most powerful energy source available. Until something learns to drink sunlight itself, and in doing so, changes the destiny of the planet forever. We descend into the shallow seas of early Earth, roughly 3.5 billion years ago. The water is warm, rich in dissolved iron and sulfur. Hydrothermal heat rises from below while sunlight penetrates from above. The sky overhead is tinted orange and brown, thick with methane and carbon dioxide. Oxygen is nearly absent, and for most organisms alive at this time, it would be deadly. There is no ozone layer to soften the sun's radiation. Ultraviolet light reaches the surface unhindered. Along the seafloor and across shallow coastal regions, microbial mats spread like living carpets. These communities are ancient, layered, and resilient. They are composed of countless microorganisms working together, sharing resources and competing for space. For hundreds of millions of years, life here has survived by feeding on chemical energy drawn from minerals, hydrogen, sulfur, and iron. This strategy works, but it has limits. Above these microbial worlds, sunlight pours down relentlessly, day after day, era after era. The energy is abundant, constant, and unused. And evolution, slow but relentless, is about to discover a new way forward. Within these microbial communities, a quiet innovation appears: cyanobacteria. They are microscopic, simple in structure, and unremarkable in appearance, but inside them unfolds one of the most radical experiments in the history of life. Using specialized pigments tuned precisely to the sun, these organisms begin converting light into chemical energy. Photons strike their internal machinery, exciting electrons and driving chemical reactions. Water molecules are split apart, hydrogen is retained, electrons are transferred, carbon dioxide is rearranged, sugars are assembled atom by atom, storing solar energy in stable chemical bonds. This process is slow at first, inefficient and fragile, but it works. For the first time, life is powered directly by sunlight, and something unexpected is released as waste, a highly reactive and dangerous gas: oxygen. At first, this oxygen has little visible impact. It dissolves into the oceans, where it reacts quickly with dissolved iron and other metals. Vast quantities of rust form beneath the waves and settle onto the seafloor in thick layers. Entire ocean basins slowly change color, unseen and immense. For millions of years, the oceans act as a buffer, absorbing the consequences of this new chemistry. The sky above remains largely unchanged, but the balance has been broken. The planet has begun to exhale. Time stretches forward. Hundreds of millions of years pass. Cyanobacteria spread across coastlines, shallow seas, and sunlit waters. Wherever light reaches liquid water, these organisms thrive. They form dense communities and build layered structures known as stromatolites. These formations grow slowly upward as generations of microbes live, die, and are replaced. Stromatolites become silent records of biological persistence, stacking life upon life over immense spans of time.
Day after day, cyanobacteria harvest sunlight. Day after day, oxygen trickles into the environment. The process is steady, relentless, and unstoppable. The oceans absorb as much oxygen as they can. Iron binds, minerals react, chemical sinks fill. Then, slowly, the oceans reach their limit. Once the oceans can no longer contain the oxygen being produced, the gas begins to escape into the atmosphere. The air, once thick with methane and carbon dioxide, starts to change. Methane breaks down in the presence of oxygen. The sky grows clearer. Sunlight penetrates more deeply. The planet's climate begins to shift. Chemistry on a global scale is rewritten. For many organisms, this change is catastrophic. Oxygen is toxic to life adapted to an earlier oxygen-free world. Cellular machinery breaks down. Metabolic pathways fail. Entire ecosystems collapse. Countless species vanish. This is not a gentle transition. It is Earth's first global environmental crisis, driven not by asteroid impacts or volcanic eruptions, but by life itself. Around 2.4 billion years ago, the transformation accelerates dramatically. Oxygen accumulates rapidly in the atmosphere, reaching levels that permanently alter the planet's chemistry. Rocks rust on land, soils change composition, the oceans shift in color and chemistry. For the first time, the atmosphere becomes capable of forming ozone, creating a protective shield against deadly ultraviolet radiation from the sun. The planet cools, weather patterns change, ice advances across continents and seas. Earth may freeze nearly edge to edge during episodes of extreme glaciation. These are some of the most dramatic climate shifts the planet has ever experienced. And yet, within this upheaval lies opportunity. Oxygen enables far more efficient ways to extract energy from organic molecules. New metabolic pathways emerge. Cells capable of tolerating oxygen gain access to vastly greater energy supplies. Complexity, once constrained by limited chemical energy, becomes possible. Life begins to experiment with new forms, new strategies, and new scales. Throughout this transformation, cyanobacteria continue their work. They do not adapt their behavior. They do not respond to the devastation they cause. They simply persist. They harvest light. They release oxygen, they survive. They do not intend to remake the world, but they do. As oxygen levels stabilize over immense spans of time, the rules of life are rewritten. Energy budgets expand, cells grow larger, internal complexity becomes sustainable, cooperation between cells becomes advantageous, symbiotic relationships become possible. Though still far in the future, the foundations of complex life are being laid. Every major biological innovation that follows rests on this ancient transformation. Multicellular organisms, movement, perception, nervous systems, awareness, all of it depends on the oxygen-rich atmosphere created by cyanobacteria billions of years earlier. Every breath taken by animals long after traces its origin back to these quiet architects of change, floating in sunlit seas that no longer exist. The oxygen in your lungs was once a lethal toxin. The light that powers every ecosystem was once ignored. Look at the world around you now. A planet wrapped in blue skies, powered by sunlight, alive with motion and sound. Forests breathe, oceans teem with life. The air itself sustains complex organisms. None of this was inevitable. It was engineered, unintentionally, by microbes that never knew your name, never foresaw forests, animals, or civilizations. They altered the chemistry of a planet simply by surviving, and in doing so, they made survival richer, more complex, and more fragile for everything that came after. We are the inheritors of an ancient experiment. Life learning not just to endure the universe, but to transform it.